you specify some subcategory here. That's what we are going to do, which will be category of perverse shifts. It should be a abelian category. So, but because again, I want to say some philosophical things that, in principle, it's very well known that it's important to be able to construct some abelian categories. So where you can take abelian category. So one is you have some algebra, and then you consider modulus of this algebra. So this was first source of abelian categories. Now the fact that so people thought that they studied algebras. In fact, the claim is that they studied category of models of this algebra. So very soon they discovered that if you have two algebras which are Morita equivalent, which means that categories are equivalent, then they have essentially the same properties. They are not isomorphic, but they so the question is how to construct abelian categories. So next thing was that you can, instead of just category modulus over some algebra, you can sheafify it. You consider some space, consider some sheaf of algebras from this space, and consider category of sheaves of models. Maybe some conditions, quasi-covariant or something. That's better. And now this thing gives some new type of constructions of non-trivial abelian categories. Again, highly non-trivial, that you consider some abelian categories obtained by previous construction, construct some triangulated categories, and then inside these triangulated categories specify some subcategory, which is not completely trivial to see that it's abelian, but it will be abelian. So there is now some new source of abelian categories, which is obtained in this way, and probably it's difficult to obtain in any more direct way. Okay, so maybe I will make a break, but I want just to say some purely philosophical thing. For me, this reminds the notion of Sobolev spaces. The idea is that if you have some manifold and you would like to make analysis of this manifold, then classics did analysis. They consider space of functions Cn with continuous derivative and so on. Now we know that if you want to get some actual important theorems, you should work with Sobolev spaces. Sobolev spaces are much more difficult to do, to just define what they are. Sobolev spaces with integral exponents, it's not very difficult, but if you consider not integral exponents, it's really difficult just to give a definition of what it is. But they are much more correct objects. So similarly here, you constructable things is something which you can construct. You can actually see what they are. And these perverse shifts are not easy to describe. So that's what the only definition I know goes to this derived category. But they are much more correct thing. And static from some point, you work only with perverse shifts, and all constructible shifts are just technical tools, which in some sense I wrote. Okay, so I think that probably it's time to make some break.
So the image of autonomic regular singular D modules is perverse shifts.
Okay, so what somebody already have written this octahedral. Okay, so what I explained is that this is some kind of motivation which shows that, at least in case when k is equal c, that this category has some nice, this triangulated category has some nice abelian subcategory. From this we can presume that probably for any K, for any field K, for example, this category also will have some abelian subcategory.
We still didn't define the ambient category for other fields.
Why?
Inside is well defined.
No, it's
The
everything.
right side we didn't define for
Deconstructible is well defined.
any field.
Yes. No.
Field of coefficients.
We consider complex algebraic variety, and we consider field of coefficients. K is just field of coefficients for instance, it might be finite field, whatever, or periodic field. Okay, so the question is: so we have category, so some fix a field K. So X is still complex algebraic variety. So we have our category D, which is D of X. By definition, is deconstructible.
A field which is not C.
Hmm?
You mean like a finite field or like
Yes.
what?
Any field. So it should be field because it's difficult to do. There should be some duality, and even if you consider over point, so it's not quite clear how to make duality. I think it's possible, but I
You take out inequality on the side.
yes, I see that this is what should be done, but somehow I don't know whether it's done or not. Deconstructible of X with coefficients in K. And now we would like here to define some category of perverse sheaf on X with coefficients in K, some subcategory of this category. So question is how to define in general such subcategory, but we have seen that it will be difficult to define abelian subcategory. It's better to define this category which is more or equal to 0 or not equal to 0. Okay, so we will do it in the following. So in fact, we will define not just this category, we will define more to this. And this probably somehow reminds me that if you have this equivalences, then you, in order to, if you have category and equivalence, you want to invert equivalences, then you better to include it into coeffibrations, fibrations, and so on. Somehow similar thing. So now let me give you the definition. So detriangulated category. So once more, the fact that it works is a little bit coincidence, because we know that the notion of triangulated category is not a very good notion. But nevertheless, it turns out it's enough to describe this thing. In principle, one could expect that only the notion of actual infinity category will
You're going to
give.
define what is T structure?
Yes. I want to describe what is the definition. Suppose that D is the definition, a T structure is a subcategory T, for instance, more equal to 0, and T, full subcategory, such that it satisfies the following conditions. First is that it's invariant with respect to T. So just T is T minus 1 point. Okay. So that's one thing. Another thing is that we can consider its orthogonal complement. Let's consider D more equal to 0, orthogonal complement. This consists of all objects C and D such that home C into D more equal to 0 is equal to 0. And then we denote this category D less than less than 0. Okay, so let's just see in our standard example. So you see, these are formal definitions, but they model just standard examples. So you have category D, which is just D A of B. D more equal to 0 will be category of complexes such that Hi of C is equal to 0 when I is less than 0. In this case, its orthogonal complement will be, it's easy to see, it's category of complexes such that Hi of C is equal to 0 when I is more equal to 0. And next property which we want is, so this category clearly is invariant with respect to T. This was invariant with respect to T minus 1, this will be invariant. And most important axiom is that for any x in D there exists exact triangle so x less than 0, x more equal to 0, where this lies in subcategory D less than 0. Yes, this lies in subcategory D more equal to 0. Okay, so now I want to say some digression which I had to say before. That from
Unique, right? It's unique.
So I don't remember whether it is required that it's unique. We'll see in a moment. Okay, it is unique, but maybe it's enough to know that it exists. Okay, so I want to remind about definition of X. Of con, so suppose I have morphism X to Y, then we construct Z, and we have seen that this Z is defined up to isomorphism, but not unique isomorphism. So the claim is that in some cases you can guarantee that it's in fact defined up to unique isomorphism. Maybe let's see what it is. Suppose I have another Z prime. So consider here identity, and here have some morphism nu. I would like to show that this, under some conditions of X and Y, I would like to show that this nu is unique. So how to show it? Suppose I have two such things. Let's consider the difference. Then you'll get morphism from X, Y. Here you have 0. Here you have 0. Z prime. Okay, so you can assume that this is 0, it doesn't matter, some delta. So I would like to show that under some conditions, if this is equal to 0, this is equal to 0, then this is necessarily equal to 0. So how to see it? So I have this morphism delta. So want to show that delta is equal to 0 under some conditions on x and y. So the idea is that composition of these two morphisms is equal to composition of these morphisms, hence equal to 0. So if this composition is equal to 0, then by exact sequence, it means that this composition comes from some morphism
From Tx on top.
from just as it goes to 0, then it comes from some morphism from
Tx to write another Tx to the right.
okay, it's just so this composition is equal to 0. This means that so I have reason, but so we apply to this exact sequence. So this composition is equal to 0. It means that it comes from that it passes. Yes. No, it passes. No, it passes here. So there exists morphism from Tx to Z prime, which. But I prefer to. Okay, I consider different thing. That the claim is that this means that there exists.
You start with composition from Z to Tx to Tx, which is 0. From Z to Tx and downstairs. No, from Z to the right.
Yes.
From Z to the right. No, from upper Z to the right.
Yes.
And downstairs. So this is 0.
Okay.
So you get that delta composed with the map from delta.
Delta
Composed with the map to the right is 0.
0. Yes.
Then it
So
comes from a map from
yes.
Z to Y.
then it comes from.
This is what you want, right?
Yes. Now, the claim is that if you, it comes from this map, but the claim is that in fact it comes from the, okay, I think that I should look at my notes. That in fact, you can repeat this now. So we used this exact sequence.
At the top it comes from Tx to Y.
Yes. Okay. So that's what I want to say. That it comes from Tx to Y. So hence, this shows that if home Txy is equal to 0, then delta is equal to 0. Okay. So I did this exercise. So this exercise. So hence, we know that if you have morphism xy and you know that home Tx to Y is equal to 0, then this cone is defined canonically. In principle, it's not canonical, but in this particular case, it is canonical. So in particular, so this has something to do with this thing. So the claim is that this triangle is in fact canonical for because this triangle you can write this is just Tx naught Tx less than 0. So I want to show that I consider this thing and would like to yes, so I would want to show that this is absolutely canonical, this morphism, and by this thing, because since we know that home of this into this is equal to 0, home of x less than 0 to x more equal to 0 is equal to 0, This was by our definition. So this implies that this triangle is absolutely canonical.
Why x?
Hmm?
How is this related to the TX? Why?
No. Since here we would like to understand this morphism. So in order to understand how canonical is this X, we should understand how canonical is this morphism. But this
But the home should be in the other direction. I mean, home from x greater or equal to 0 to x smaller. Right?
just one moment. X less or equal to 0.
The problem is that in that case the home is not 0. Yes. The requirement.
Just saying that.
Yes, but
Okay.
if you replace them, then the home is not 0.
Okay, so okay, I don't remember. So okay, so important thing is that this cone is uniquely. In this case, in this particular case, this cone will be uniquely defined. So this decomposition X. So you start with any X, then the claim is that X, it has some such decomposition. And the claim
Are you
is,
working with the H category or an arbitrary triangulated category?
so I'm working with arbitrary triangulated category, and I consider T structure on it. And T structure, by definition, any X has such a decomposition.
It is
The claim-
factorial X?
Hmm?
The composition is factorial.
Yes. So this decomposition is factorial.
This is
Yes, this is a statement.
So you
Okay.
assume existence give you factorial.
Yes. Okay, so now let me describe what is category of perverse shifts in this description. Yes, so in that, if you have, so given a T structure, so D more or equal to 0, and D less than 0. Now we can also describe the D more equal to I. It is just T to the I, or minus I, whatever, T more equal to 0, and similarly T. So, and then we, given T structure, we define Hartord's structure of T structure is just intersection of category D less or equal to 0, intersection T more equal to 0.
The full subcategory.
Yes, it's full subcategory, which is intersection of these two. And the claim is that it's, if you have T structure, it is an abelian category. And this is models our discussion. So this is the way how to construct abelian category inside triangulated category. You should construct this T structure. So in order to construct T structure, it is enough to construct one of these categories. Another is defined as its orthogonal complement, and conversely, this is orthogonal complement. It's easy to see from this existence that this is orthogonal complement of this. It's,
Saying this from his accent follows that
Hmm?
from his accent they're saying it follows that it's multi-abelian.
what?
And this
Yes.
is
Yes, from this follows that it's abelian, and it's very easy to understand. So understand why. The idea is that you have x to y. What does it mean abelian? It means that it has kernel and co-kernels. So what's you consider cone of this, and then consider tau, whatever, less or equal to 0. I don't remember. have truncation. So this operation is just truncation. So you consider you consider arbitrary morphism from X to Y, consider con of this morphism, and then consider its, I don't remember, tau less or equal to 0, tau more equal to 0. It gives you element. The claim is that it will lie in our heart, and it will be kernel or co-kernel of this morphism. Okay. Okay, and so now the category of perverse shifts is defined just in the following way. You define so we want to define category T structure, perverse T structure. Okay, so I have some F, derived category of constructible shifts on X. Then it is locally constant with respect to some stratification. So find stratification.
By definition, stratification should be analytic or something.
Algebraic. No, stratification, we consider algebraic variety, we consider algebraic by non-singular, if you want to find, it doesn't matter, by S equal Si, smooth strata of dimension I. So Si of dimension I, maybe it's variety which is smooth, maybe not connected. So it has several components. So when you consider F dot restricted to Si, this will be locally constant. So you can always find such stratification that this is locally constant. So if it is locally constant, it means that everything is controlled by fibers. And the condition is that Hi of, so if you consider some point X in Si and consider Ix star of F, which will be just complex of vector spaces, that you want that its homologies are equal to 0 if I is more than dimension of, excuse me, if, okay, I'm P. If P is more than I. So, for example, what is a constructible sheaf? Constructible sheaf means that if you restricted to this stratification, then at every point, its fiber will be equal, cohomology will be equal to 0 when I is more than, when P is more than 0. No, I don't know, one moment, I'm defining D more equal to I, or probably I'm defining D less or equal to. I'm defining what is D less or equal to 0. So this will be mine.
The homology is more than the dimension.
Yes.
Dim Si.
Yes. So if you do it, if you consider constructible T structure,
This should be. No. Si is dimensional.
So if you consider constructible T structure, so first of all we have constructible T structure, which we discussed before. Constructible. Then you can define that F lies at D less or equal to 0 means that if you consider f restricted to Si and consider fiber at every point, then HP of this will be equal to 0 when P is more than 0. So at every point, all cohomologies are concentrated in not positive degrees. And here we slightly modify this condition, namely when you consider it on strat Si, then we require that it can have some positive cohomologies, but not too much, not more than I.
So shouldn't it be the codimension of the strata? I mean, we require less from points than from the general point.
So it should be, as far as I remember, it is dimension.
Want to require more.
So here, for example, on the open strata,
Yes,
going
yes,
to
yes,
be
yes. No,
Anything by semi-continuous?
just one moment. You're correct. So here we consider P more than equal to minus I. So it means?
Basic misunderstanding. You write two conditions, one P bigger than 0, and the P bigger than minus I. So then example.
No. This is for different. This is for so you have two different T structures. You have deconstructible and deperverse. Constructible T structure and perverse T structure. So in constructible T structure, you just write that for any fiber, HP is equal to 0 when P is more than 0. That's easier. And for perverse T structure, you write that, you're correct, that it's equal to 0 if P is more than minus I. So for instance, let's consider n-dimensional non-singular variety. That
Claiming is 0 or non-zero is the same.
what?
In one case, you take first inverse image to
You can take twice in those images the same as take one.
But
Just five.
fibers.
No, but one time you take homology
Fiber
and then
over
fiber,
the
and the
fiber.
second time you take fiber and then homology.
It's the same. The
So
same.
that was the question.
Yes. Okay. This fortunately is the same. So, for instance, what does it mean? It means that on open orbit, and you have n-dimensional varieties, on open orbit, you have that it is concentrated in dimensions less or equal to minus n. So in particular, if you have perverse shifts then on open orbit, it will be in dimension, cohomologies will live only in dimension minus n. So it should be shifted. So why it should be shifted? Because we want also this to be invariant with respect to Verdier duality, so it should be shifted. Yes.
This means that F is in D smaller or equal to 0.
Yes. This means exactly condition that F is in D less or equal to 0 perverse. So this is exactly the condition. Now, if you want,
And of course, D less than or equal to 0 perverse belongs to
yes, it belongs, but it's completely irrelevant. Okay, this is correct, but I never seen this used in any way.
Just to remember, what are the conditions, what are the sign, correct?
No, just okay. No, so I want to write somehow minimal set of conditions because okay, so okay, but the idea is that this defines as some defines as T structure, and so it defines so that if you consider so claim this T structure. This is T structure. Moreover, it is, that's first. Second, that it is invariant with respect to Verdier duality. Now, what does it mean that it's invariant with respect to Verdier duality? It means that Verdier dual of D less or equal to 0 will be D more equal to 0. Perverse. In particular, the intersection will be invariant with respect to Verdier duality. So D maps perverse shifts into perverse shifts. So next thing is that, so I will see how much we will prove of this. So next statement is that this so perverse equal intersection is a abelian category, and for that every object has finite length. And fifth, we'll discuss some kind of classification of irreducible objects. Okay, so this is the definition, and if you look at the definition of perverse shift, in most of the book it's written that perverse f in D of x, and f is perverse if I star of f is concentrated, Ix star of x for x in Si, I is concentrated in dimensions less or equal to minus I, and I chic x of f for x in Si is concentrated in dimension more equal, I don't remember, I or minus I, probably I, yes, in dimension more equal to I. So this is correct definition, but it's equivalent to this one, so it's easier to work with T structures than to work with this definition. Okay, so yes.
Dimension at most minus I?
For I chic, okay, I don't remember. So here, yes, minus I, yes. So it means that, okay, so if you have a local system, then on dimension n, then it should live in dimension minus n. It's so perverse shift. If you have locally constant perverse shift on non-singular variety of dimension n, then it should be concentrated in degree minus n. Because you want this notion to be invariant with respect to Verdier duality. What?
So we have a complex of constructible shifts.
Yes.
They know how to be stratified, or I choose it in some way, or it's
No,
independent.
so the claim is that it doesn't depend on stratification, of course. No, you can easily, okay, so let me give the same condition, for instance, this condition. This means that the set of all points, x and x such that hi of ix star of f is not HP is not equal to 0.
Dimension of this
Is equal not equal to 0 for fix some I. No. So the claim is that this set should have large co-dimension. That's just you. It's just equivalent condition. You can just evaluate. So this is just. I remember this.
Stratification. The condition, if it satisfies the condition, it gives you the stratification.
No, it doesn't give. No, there is no canonical stratification. If you have any stratification, you can consider smaller stratification. Yes, it gives you.
But it doesn't give you certification that the restrictions to the strata will be smooth. They might be not smooth. If the shift is perverse, then yes, but if it's like hard perverse, then no. But
No. So just I'm saying that this condition, which depends on choice of certification, you can write down in form which doesn't mention any certification at all. Just the set of, consider the set of all points where HP of this thing is not equal to 0. Then the claim is that this set has sufficiently small dimension. So it's just equivalent. So so the idea is that if your shift is constructible, then this set is automatically constructible set. It's just union. So if it has some stratification, then it will be union of strata in this stratification. And that you just purely formally you write one thing or another. So just in this formulation, the reverse stratification is not mentioned. But it's easily equivalent one to another.
when you say the right category, so all those objects in the right category, you mean bounded right category, arbitrary right, is it like unbounded right category, you don't care?
I personally always consider the bounded category.
And the posterior, even if you don't consider bound, the perverse shift is going to be bounded, yes?
Yes, perverse shifts are definitely going to be bounded. It's more or less clear from these formulas. Yes, yes.
Yeah, because of
Yes,
half
because
category is not going to be bounded. Like
what?
the T structure, the half of the category with respect to perverse T structure,
it's
not going to be bounded if you don't demand that.
It's not important here.
But it's not
So I didn't
So
understand.
the category is B less than equal to 0 perverse, doesn't have to be
No, it doesn't have to be bounded. No, you can consider infinite complexes, but it will be bounded above. And when you consider another condition, it will be bounded below. That's
The stratification can be not smooth, right? It doesn't have to be smooth.
no, stratification will always assume that it's smooth. So strata we always consider to be smooth, smooth algebraic varieties. No, for this condition, it doesn't really matter. But no, because you see, the idea is that when you write Si, and this is less or equal to minus I, what does it mean I? So the idea is that when variety is not smooth, I prefer not to talk about its dimension at all. So there's no such thing. So if it is not if it is smooth, then its dimension is well defined. Otherwise, it is problematic. You can give formal definition, but it's geometrically, because it can have two components. No, so here the idea is, for instance, when you work with D models, it's Categorical Shifts, you should normalize everything very accurately, because if you have algebraic variety which has two components, one of dimension 5, another dimension 3, if you choose wrong normalization, then you'll get some strange phenomenon. And this is because these two components they don't have, for instance, they are disjoint, but then they're moving, they start have common points. So if you choose orthogonal normalization, you suddenly see something inconsistency. So, stratification, we always assume that it consists of non-sequential strata.
It looks like every perverse, to me,
Yes.
every perverse sheaf is constructible, but you said that's wrong.
No. Every perverse sheaf is complex. It is complex.
The guy and it's orthogonal, right?
I see.
Yeah, this guy belongs to
That's
them,
the
but
T-square, I see.
orthogonal is greater than
Yes.
so intersection is
Yeah,
somehow
I see.
shifted. This is what Joseph meant when he said that this
No,
is
so just if you have n-dimensional smooth variety and you have perverse sheaf which is locally constant, then just local system shifted in dimension -n. It's just the same thing. So perverse shifts which are locally constant are just local systems shifted in dimension -n. That's it.
Is this local condition of being perverse?
Yes, of course, it's defined completely locally. So in moreover, this is abelian category. So if you define it, if you construct some perverse sheaf locally, then it automatically will. Since it's abelian category, it doesn't have this problem which has derived category. In derived category, if you construct object locally, it's not clear how to construct it globally. For perverse sheaves, if you have some actual construction which locally works correct, then it automatically gives you perverse sheaf because it's abelian category. So in this sense, it is as good as constructible sheaves because they also form.
So a perverse sheaf which is locally constant is shifted by a local system.
Yes, on non-singular variety.
On a non-singular. So
Yes.
if I have a curve and I have a
Yes.
perverse sheaf which is locally constant, then it's like
It's just local systems in dimension -1. That's all.
I see.
That's just completely equivalent.
And a general perverse sheaf will have, on an open set, it will be like a
Yeah.
projection, and on a finite set of points, we'll have
So will be
singularity.
something. We'll discuss what we'll see.
And in the course,